Go team. Spin. That's the name of the game. So to make sure that everyone watches this video, which is so unbelievably cool about the Stern-Gerlach experiment, I'm going to share my screen and play the video for you. Ha, you are held captive. All right, share screen. Desktop 1. Yes. Share. Okay, whoops. Close that out. Okay, so here we go. This is the Stern-Gerlach experiment. You've got bar magnets here, spin a quantum magnet. Go team. I'm just going to let it play, let you watch. Play. There we go. Oh, spin up. Or I should say bar magnet up. Is sent with pull up and pull down. Device creates a force which deflects the magnet upward. Awesome. If it's in the middle, it goes down. If it's all sorts of different orientations, now you see the deflection, you have all these various orientations available. Go team. That's with a bar magnet. Same idea. Silver atoms. When silver atoms go through, oh, up or down, oh, up or down, oh, oh, up or down, oh no! Only have up or down. You don't have the other variations. What could this mean? It behaves as a magnet, but it can only be one way or the other. The quantum property of spin. Go team. That was cool. I will post that video on Moodle. Okay, so spin. So that was a Stern-Gerlach experiment. It's very difficult to do. They used silver atoms. That was a fun exam question I gave years back. It was, why did they use silver atoms? It trumped everybody. It was funny. I mean, not funny. We worked on it, and I was like, oh, think about it. Go team. We have quantum numbers, N, L, and M sub L, that come from, you guessed it, funny story. When I taught at OU, I taught PChem, of course, and my students always either, they gave me, this happened twice actually, something that had an equation on it that they were like, oh, you are gonna love this. That and delta S is increasing because, you know, delta S is increasing. Anyway, H psi equals E psi. There's only so many wave functions that you can get when you operate the total energy operator on the wave function gives you the energy of the system, okay? So, and these that satisfy the system, or I should say Schrodinger, yield the quantum numbers. In L and M sub L. Principal, angular momentum, magnetic component of the angular momentum. Cool. Stern-Gerlach shows that there is an additional quantum number, and that's in spin. And it's intrinsic to the electron itself. It is not affected here, as in you don't find it within the wave function. This is something that has nothing to do with the boundary conditions. Cool? So there's an additional quantum number that we need, which is called S, and not affected by the boundary conditions. How the hell do we know it's there? Pauli, that's how. So Pauli was really stuck on the Zeeman effect, which will be atomic splitting, or atomic spectra splitting that you'll see, where the difference in the energy state was actually too small to be the difference between this energy state and this energy state. It was like up here. So there's very, very subtle differences. And that originated from spin-orbit coupling, which we will get to, but we gotta talk about spin first. Okay, so let me give you the picture. Okay, so here's our electron. It's around the nucleus, right? Okay, so there's an angular momentum associated with this electron going around the nucleus. And so it has some sort of J value, which the magnitude here is equal to L times L plus 1, all that 1/2 h bar. So that's the magnitude. This is going to be m sub L, and that can be plus or minus values of L. And that has to be either 1, 2, and so on. And depending on the length here, you're going to have, so if L equals 2, then however the orientation is going to be such that the projection of that vector onto the z-axis is going to be unit values of plus 1, plus 2, minus 1, minus 2, 0. Okay. L and m sub L. Check and check. Same picture, zoomed in. So now we have spin quantum number S. It has, so the electron is charged and moving. So because it's moving, it's accelerating, which means it's changing direction. You have a positive or possibly negative dv dx. So the first derivative of the velocity is an acceleration. If a charge is accelerating, it is creating a magnetic field. It's moving this way, so it's creating a magnetic field. So there's a magnetic component that originates from the charge itself. You can kind of think of it as orbiting around the electron, but it's not really orbiting within the electron. Anyway, so this spin has magnitude of s plus 1, 1/2 h bar, and its projection onto the z-axis. Any guesses what that value is? Or m sub s minus 1/2. So plus 1/2 or minus 1/2, above or below. Okay? And so its quantization of space happens to be only plus 1/2 or only a minus 1/2. It can't exist in between. And unlike with the angular momentum, where you can have -2, -1, or +2, +1, 0, and so on, depending on the degree of your angular momentum, L, S, you only have plus or minus 1/2 options. Cool? Okay. So the other thing I want to talk about is electrons are fermions. Oh, sorry. Other thing before we get into fermions. So the multiplicity, which means how many of these are there, for L, you have m sub L equals L, sorry, totally lost it, 2L plus 1 equal the number of m sub L's. So if L equals 2, which is a d orbital, then you have 2 times 2 plus 1, which means you have 5 orbitals. 2 electrons per equals 10 electrons in the d orbital. Cool? You're happy with this? Yes. Multiplicity. So that's the multiplicity. The number of m sub L's that you have is called the multiplicity. For spin here, you have 2s plus 1. But Stern-Gerlach showed that you only have up orientation or down orientation, which means you have 2. What does s have to be? In order to satisfy this equation, if you had any sort of orientation from the Stern-Gerlach, this could be any number, but it's not. It's only 2. It would be either up or down. So that means s has to be 1/2. That's how we know what those are. Okay. Other thing. You can pause me if that needs to sink in. Go team. The other thing about this is you can have, so there are 2 types of matter, fermions and bosons. Fermions are spin half, bosons are spin whole. So fermions have half integer spin, and bosons have integer spin. So electrons are designated as fermions, photons are designated as bosons. This is how you can have a superposition of light and you don't have any effect. It can occupy the same space. Fermions, however, you can't have one atom occupy another atom's space. Just like with fermions, also you can't have spin up and spin up in the same quantum state. You have to have spin up and spin down. Pauli's exclusion, you already know this. Cool. I think that's all I want to say about spin. It's not a top spinning. Don't think that. It's the intrinsic angular momentum magnetic component of the charge moving of the electron that's then moving this way. Cool? And pretty soon we're going to have spin orbit coupling where this magnetic moment and this magnetic moment couple together. Go team. Bye. Okay, that's all I got. Spin. Yay, spin. Stop.